Okay, we are going to start on momentum now. And guys, we're not going to get crazy on momentum. You should know that when I teach physics, momentum takes a whole chapter. A lot of stuff actually in chapter 2 does. So we're just kind of basically touching the surface of momentum. It is related to Newton's second law. So, where we have force is equal to mass times acceleration, there is some relation to that for momentum. But what you should know about momentum is this is kind of the definition, is that it's affected by both the motion, so the velocity, and the mass. Okay, so this is your equation for momentum. And I don't know why momentum has the symbol P, not to be confused with rho. If you remember right in chapter 1, rho looks like a P, but it's not. So momentum has the symbol P, and this is mass, and this is velocity. Okay? And we'll get back, maybe I'll come back to some of these values here on the bottom here in a minute. I wanted to kind of talk about conservation of momentum because that's really the main concept that I want you to take from momentum, is that there's conservation. So what does that mean? That means that it's not lost, okay? It's just conserved. So the total amount of momentum in a system remains the same. So for instance, what happens if you shoot a gun here? Like, this is a rifle, so it's gonna, if I was in class, I'd show you I don't shoot a lot of guns, but I do know that when you shoot a rifle, you kind of put this back part here against your shoulder, and you really want to keep it there tight, otherwise it could kind of like come up and smack you in the face, right? And so whenever you shoot the gun is going to kind of go backwards. Well, the gun has a mass, doesn't it? And it's also going to go backwards at a certain velocity. Where this bullet here, it also has a mass. Now, which one has the bigger mass? Well, obviously the gun, right? And so because of that, its backwards velocity isn't going to be as fast. But that bullet has a much smaller mass, and its velocity is going to go super fast. So this whole system right here has a conserved momentum, okay? The backwards gun and the forwards bullet are the same, okay? All right. And this right here is just showing you that you could take this astronaut that's going, it looks as if it's going to go forward, but it sort of looks like it's touching that satellite and it's causing that satellite to go forward, and then that's going to cause this astronaut to go backwards. And looks like that the mass of the astronaut's 60 kilograms and its velocity is going 0.75 meters per second. And then this mass of the satellite's twice, the amount of the astronaut, and its velocity is about half. And if you do the calculation of mass times velocity for momentum, they're the same. Okay, so again, you have this conservation of momentum. And if you're hearing something right now, it's because I'm going through my book really quick, seeing if we have an example. And I think we do, but I could be wrong. Yeah, we do have one, but it's a little bit more involved. So let me show you the example really quick in the book, and then we'll kind of work it out. Now, most students don't like this example, so I apologize in advance. All right, so this is example 2.14, and this is showing momentum, but a little bit different because this is showing what happens if things are combined. Okay, so this is saying a 20,000 kilogram railroad car is coasting at 3 meters per second. When it collides and couples, that means that it's stuck together with a second identical car at rest. What is the resulting speed of the combined cars? Okay, so I'm gonna pull up maybe my note thing over here. Come on, there we go, so that I can write this out with you guys. So again, I would have my PowerPoint out and be writing this on the side if you can. And then always write down what you're given. So we've got a 20,000 kilogram car is coasting at 3 meters per second when it couples with a second identical car at rest. So if it's identical, then that means that it's also 20,000 kilograms. But what is its speed if it's at rest? Well, it's 0. Okay? All right, so this is conservation of momentum is kind of when we say, we kind of do it like this. We say momentum is equal to momentum because we're saying that the momentum before is equal to the momentum after. So this is like before and after. Okay? All right. So stick with me. So we've got mass 1, velocity 1. Okay, this is the first car. Plus mass 2, velocity 2 is equal to, now, what happens when the first car runs into the second car? Well, they stick together. So you have mass 1 and mass 2 times both. Like this is their overall velocity. Okay? So you've got mass 1. I'm going to start filling out numbers here. So you've got mass 1 times velocity 1 plus mass 2, which was 20,000, times velocity 2, which was 0. Well, what's anything times 0? 0. So we can kind of cross that one out. Is equal to mass 1 plus mass 2. So we've got, I'm kind of writing this over here now. Mass 1 plus mass 2 times the velocity of 1 and 2. We don't know what that is. That's what we're trying to find. Okay, so I'm going to write this a little bit differently. Okay, because I want to kind of shorten it just a tad so that you guys can kind of see what I'm doing here. So if you take 20,000 times 3, you get 60,000. And let's talk about units for a minute. You have kilograms times meter per second. Does anything cancel? No. So this right here, that's a unit for momentum. So something that you need to kind of know, okay? And then 20,000 plus 20,000 is just 40,000 kilograms. And then we don't know what this is. This is what we're trying to find. So how do I get this velocity 1 and 2 right here by itself? Well, I gotta divide right here. And that's gonna cancel that, and it's gonna cancel that unit right there. So if you take 60,000 divided by 40,000, you're gonna get 1.5 meters per second. So after those two cars combine, you're going to end up with, a velocity of 1.5, which, if you look at this example right here, it ends up putting it as 2 because of significant figures. So 60,000's 1 sig fig, 40,000's 1 sig fig, so that's where you end up with that 2 meters per second. Hopefully that makes sense. It's kind of a, it's kind of a tricky one, but just kind of know what that momentum has the symbol P. It's mass times velocity, so kilograms times meter per second, and that you can kind of equal the before and after like this up here and set it up sort of like we did in this example, and you should be okay. All right, I'm going to go back to our PowerPoint now so we can talk about impulse really quick. So impulse is a force that's acting on an object for a certain amount of time. Okay, so remember how we had said that momentum was somewhat related to Newton's second law. So force, obviously is in Newton's second law. And momentum, okay, or impulse, I should say, is force is equal to the change of momentum divided by the time, okay? And change of momentum means that it could be final momentum minus initial momentum, okay, over time. And I just want to point out really quick, if you take momentum, the equation for momentum, and say mass times velocity over time, and you just take this little section right here, velocity divided by time. Well, if you remember right, velocity divided by time, the change of velocity, I guess I should say, divided by time, is acceleration. Whoops. Did I do that? Oh, gosh. So force is equal to mass times acceleration. That was Newton's second law. Okay, but momentum and impulse uses this equation. So it's just something that throws in force into a momentum situation. So, and if you think about it, like even looking back, at this gun situation, do you think there's any kind of force that's involved? Absolutely. So if you couldn't find the momentum using the mass and the velocity, you could possibly find it by finding the force and the time, okay? And you'd still be able to find the momentum. So, okay, I'm going to stop because I don't want to do circular motion on this video, and then we'll do another